Welcome. I want to basically give you a demonstration of two of the specific applications included in Whetstone Technology's Stego suite, specifically StegoHunt and Stego Analyst. Let's start with StegoHunt, but before I do that, I want to actually show you a directory that I've created with some sample files, just to basically show you what that looks like. I've got a bunch of Stego applications and a bunch of files that are potentially stegoed or not stegoed, actually before and after, images, audio files, videos that have been stegoed with certain applications. And again, some directories that contain some known Stego applications, just to kind of show you how this is going to operate. So the first application I'm going to show you is an application called StegoHunt. And what StegoHunt does is it allows us to do two fundamental things. First, it allows us to scan for known steganography programs. There are well over 1,000 programs within the StegoHunt library that are known steganography programs that are out there from various genres, whether it's Windows, Linux, Mac, mobile devices, as well as technologies that have spanned multiple decades. So any of the older programs or the newer programs that are part of that file. So what I'm going to do is, instead of scanning a whole drive just to keep the demonstration quick, I'm going to basically add a directory. I'm going to go to the desktop and I'm going to select Whetstone as the directory that I want to scan. So it's going to scan that directory and any of the subdirectories associated with it. If there were any archive files included in that directory, which there aren't right now, it'll scan those and unwind all of those archives as well. Once we do this, we have two options. We can scan for programs or we can scan for carrier files. In the initial demonstration, I'm going to show you how to scan for programs. These are the potential applications that exist. So once I've selected the directory that I want to scan, kind of see that it was my desktop and the subdirectory Whetstone, and any subdirectories below that will be scanned. And I'm going to go ahead and scan the programs. This happens relatively quick because we're doing hash matches of those. It pops up and asks the investigator name. We'll just call this demo 001. I'm going to actually place the resulting files right on my desktop so that I can have easy access to them when we actually generate those, so we can actually see an investigator report as well. So I'm going to say confirm. It's going to go out and perform that scan, and it does that relatively quickly. And notice we've got 15 hits that were detected of known steganography programs within that directory that we're scanning. I can take a quick look at the results by clicking the results button, and that'll give me basically a list of the files that we found and a bunch of details regarding the file. For example, in the first entry, we found a program, Jpeg Hide and Seek, and we found the actual file that's associated with Jpeg Hide and Seek called jphide.exe. You notice that we also found Jpeg Hide and Seek win.exe and jpseek.exe. All of those files are associated with the Jpeg Hide and Seek application. For each one of those, we record the modified access and created times. We get the MD5 hash, the actual path of the program, the file size, the original file name. So if somebody were to go in and change the name of the file, we'll basically tell you what the original file name was within the application that we've actually determined, where it was, and the source of that information. So that allows us to do that. In the case of MP3 Stego, in case of S-Tools, there were multiple files found that were associated with S-Tools in this particular scan. Again, each one of the files are identified, and all of the information regarding MD5 hash, the original file name, are all provided for you. We're also going to get a report that we can take a look at as well. That's more of an investigative report versus a quick result scan. So let's take a look at the actual investigator report that's associated with the program scan, or the scan program function. It created a directory on my desktop, and I'm going to go ahead and bring up that demo 001 file. It's basically going to give me a HTML report giving me information about the investigator, when the scan took place, how long it took, how many hits we detected, and then for each one of the files, the same kind of information that we found in the screen or display-based report is included here. the MD5, the file name, the program, the last access, modified and created times, the path, the file size, and again that original file name, which can be important. So that's done for all of the hits that we detected during that particular scan. So you have an investigator report as well as a quick way to display that on the screen using the display option within StegoHunt. Now that we've identified that our files within this particular folder that are Stego-related tools or programs, we want to actually take a look at those images, audio, and video files that are included within that directory in order to determine if there's anything suspicious there. So we're going to use that same directory, but this time instead of scanning for programs, we're going to scan for carriers. Carrier files are files that would carry information hidden within that content, whether it's an image, whether it's an audio file, whether it's a video or some other format. We want to be able to detect if anything has been embedded within that particular application by running specific algorithms within StegoHunt that will identify those types of anomalies that we would normally see from those types of embedding. So in this particular case, I'm going to run the same scan, but I'm going to click on the Find Carriers button. When I do that, it's going to give me the same screen. I'm going to put the results in the same location, so I'm going to do this. This scan takes a little bit longer because we're actually having to look at and take a deep dive into every single one of those images, audio files, videos that are there in order to be able to determine if there's anything anomalous or unusual within that, and then if there was, what were those anomalies. So that's completed. It found 15 different hits regarding the carriers. And again, we can take a quick look right on the screen by looking at the results button. So this output is just a little bit different than we saw from StegoHunt, the program search, because now we're actually looking at specific files that contain hidden content information. So in this particular case, we found Angel stools.wave. It was a carrier anomaly, and it was statistical, meaning that we calculated statistics on that particular file, and we found anomalies that are relevant or related to the hiding of data within that information. So again, we get the same kind of information, modified access and created time MD5. We also provide a detection code that you can look up in the user manual to give you more information about that particular detection. Again, if you need more information, you can slide these over. The next detection is interesting because we found the name of the file was browser.dll, but we found file extension obscuring, meaning that that particular file is actually a JPEG. It's actually not a DLL. So in this particular case, it found a signature that this file was had an improper extension on it. Moving down the list, we found a file called container.mp4, which is a movie file. And in this particular case, we identified a structural anomaly that is associated with a known Stego program called TC-Steg that basically hides information within a MP4 file that is actually a TrueCrypt volume, an encryption program that they've embedded directly in that. So we've identified that as well. We identified limo.camo, which I'll show you in a minute, that has data appending. So in other words, there was information appended at the end of image marker within this particular JPEG. Now we have carrier anomalies for several of the BMP, GIF, WAV files that have carrier anomalies, meaning that we performed statistical analysis of those and found anomalies within the image or audio file based on the algorithms that we run against those. Finally, there's some other programs here that we had file extension obscuring or carrier anomalies within those as well, which we'll take a look at those when we actually move to the application Stego Analyst. We can actually visualize some of this information that's there, but it's a way to basically scan a group of files, whether it's a file system, whether it's a directory that you want to scan those particular files, you can, and we'll give you definitive results as to whether or not there are anomalies related to data hiding or steganography within those particular files. Now that we've completed the automated scanning aspect, we want to do some manual review or analysis of the images and audio files that we found within that scan that we performed. So I'm going to exit out of StegoHunt, and I'm going to bring up an application called Stego Analyst. And so I'm looking at that same directory that we had earlier, and I'm going to actually analyze some of the images and audio files that we had here. Let's start with something really simple. I'm going to take a Mona Lisa BMP file, and I'm going to side by side display an image of the Mona Lisa that has been compromised. In other words, information has been hidden in the second image. If I connect these two panels together, and let's say even zoom in about 400%, we can look at these two images side by side to compare them, noting that the image on the left is the original, the image on the right is the one that contains hidden content or hidden information. There are a couple of important parameters that we would look at when we're actually comparing two images like this. One is, what is the size of the file? You notice that the file is 402,678 bytes in the original, and it is exactly the same in the hidden one. It's because least significant bit embedding was used in this particular raw image in order to hide or alter data which is in the least significant bit of the colors that are associated with the Mona Lisa image. What that does, however, it changes the number of used colors. By making modifications to that least significant bit, the information contained there creates brand new colors. So you notice in the image on the right, there are more colors than there were in the original because of that alteration of the least significant bit. But we can do a little bit more here. We can actually, let me blow this up a little bit. We can actually run a couple of other renderings of this particular image. So for example, I could do image transformation, and I could look at intensity, saturation, but let's look at hue. When we look at hue of these two images, we're starting to see some differences by rendering this image differently. So instead of rendering it as a normal image like we would see it where they looked identical, now we're starting to see some distortion and some anomalies in the visualization of the rendering of hue. And this is because the alteration of that least significant bit has affected the hue angle of these particular pixels within the screen. And obviously we can zoom in farther if we want to actually take a look at these a little bit closer to see some of the anomalies that we have, for example here. The problem with this is that even though this is a good indicator that's there, it doesn't provide us with looking at the actual way that information was hidden in this particular image. So we're kind of looking at, if you will, a second order artifact of that particular image. And I want to look at the first order artifact of the image. Let me disconnect the panels for this. So what I'm going to do is I'm going to take this image on the left, and what I'm going to do is I'm going to render this image instead of a 24-bit true color image. I'm going to render it as a 1-bit red image. I'm only going to take the red pixels and I'm going to render those to see if there's any legitimate information, if you will, within that least significant bit of the red image in order to be able to determine if we have enough information. And you can kind of see that we can sort of make out a little bit of the Mona Lisa face and the chest of there where there are some red colors. And so there is legitimate information in that least significant bit that we can render. The question is the image on the right, when we're rendering that, what if we do the same thing? Knowing that least significant bit steganography hides information in that least significant bit, we're expecting to see more significant changes. So if we do it here, we do in fact see this dramatic change in this particular image because all of those least significant bits that were empty here actually contain hidden information that's definitively identifying the steganography. So that's a really simple one and an easy one. Let's take a look at another one here. We're going to take a look at the limo and the limo camo. This particular image is going to look identical because there's been no changes made to this JPEG at all except for information hidden at the end of file marker. So in this case, we're going to actually look at the hex values of the image itself. And the way JPEGs work, they start out with FFD8, which is the beginning of image marker, and FFD9. If we go all the way to the end of the file, we notice that we have FFD9, which is the end of image marker for that particular file. If we look at the image on the right, the one that was Stego, information was added to it, we notice the FFD8 beginning of image marker. If I go to the end, however, and go to the end of the file, I notice the end of image marker is not here, meaning all of this data was appended after the end of image marker, which doesn't affect the way the image was displayed because it's basically ignored by the programs that would in fact render this particular image. So if I go back to the file view, we can kind of see some of this information that's important here, because in this case the original image was only 8,027 bytes. The image on the right was 348,879 bytes. A very significantly different in size for an image that's exactly the same view. So again, something that we want to look at between those. Let's take on another example here, and actually let's look at this GIF image. So again, to show that we can process different images. And when we do that, the bottom part of the screen changes based on the image type that's being displayed. The kind of information, for example, we might want to look at within these images is going to be different, whether it was a true color BMP or whether it was a paletted image like a GIF or whether it was a compressed image like a JPEG. The kind of information that we're looking for and want to see is different, so the application adjusts to that specific file type. So one of the things that we might want to look at in this particular image, again, let me connect the panels together and we'll zoom in a little bit. And we can kind of see these. Now, because this is a paletted GIF image, we do see differences in the before and after image. It's more distortion. And the reason is that some of the pixels, some of the palette information is duplicated here in order to be able to hide the information. That's how the Stego programs do that for paletted images. We can see that by looking at the used color palette. You kind of notice in the used color palette in the image on the left, there's a lot of variation in the colors that are being used. But in the image on the right, there are a lot of close colors. You would never do this with a paletted image normally because there is no different. We're not able to distinguish the difference between these very, very close color pairs within the image. Our eyesight is not good enough to determine those. So you would want to use the most diverse sets, and so you only have a limited number of palette colors to use. You would want the greatest diversity in those. You can kind of see these are very close. If I look at the close color pairs, you notice there are no close color pairs that were identified in the image on the left, but in the image on the right we found 8 close colors in 32 different bins. This is a direct signature of how STools actually hides information within a paletted image. Now let's switch gears a little bit and let's take a look at something other than an image. In this particular case, let's look at a raw WAV file, an audio application, and we see the traditional waveforms of this audio file. Again, image on the left, or the audio file on the left that's being depicted in its waveform is the original. The image or waveform on the right is the image of the one that has hidden information in it within the least significant bit of this WAV file. Again, this is a raw file very much similar to a true color BMP, where the least significant bit of the samples are being adjusted versus the least significant bit of the colors that were being adjusted within the images. So in this particular case, when we look at this waveform at a glance looks pretty similar. But the question is, what if we look at these silence areas at the beginning of the song? Let's take a look at the first 1,000 samples, which is only a fraction of a second that typical songs have a silence area at the beginning of the song. And you notice that the waveform on the left, which is the original audio waveform, in this particular case, there is no data. In other words, all the values of the samples for the first 1,000 samples are 0. The question is, what are they for the first 1,000 samples of the audio file that has hidden data in it? And you notice there's data here. And more importantly, we notice that the data is either a 0 or a 1. If I bring that down to, let's say, 50 samples to give you a better idea, the data toggles between 0 and 1. This is the actual binary data that was added in this file by modifying the least significant bit. And this continues throughout the entire song, but we detect it by looking at the, we visualize it by looking at the initial silence area of the song. So that kind of gives you an idea of how we actually perform the analysis. Obviously, the algorithms that we use to detect this actually are calculating entropy for that least significant bit to basically determine if there's anomalies in comparison to the rest of the song. So finally, let's take a look at a JPEG image. which is certainly a common image that folks are going to use in order to hide information because it's the most popular image on the internet today. There's trillions of images out there, so if anyone is going to hide something and you want to hide the proverbial needle in the haystack, you would be obviously using, from an image point of view at least, would be using a JPEG image as the most common way to do that. So let's blow this up a little bit so we can take a look. Let me make sure that the panels are in fact connected. They are. So let me zoom this in a little bit so we can get a closer look at this particular image of the Colosseum. And again, the two images, on the left is the original, the image on the right contains the hidden content. And you notice in this particular case, the image sizes are different. And they're different because once I make changes to a JPEG file, compression occurs, and the compression is going to be different based upon the information that's hidden in the image. It's going to cause a change in the size. And in some cases, like this one, you notice that the size of the image that has the hidden data in it is actually smaller than the original. Somewhat counterintuitive. But it doesn't matter. Based on the information that was being hidden caused the compression to be more successful and more dramatic than it was in the original. So at this point I might want to actually look at some of those image filters. In other words, looking at rendering this image a little bit differently. So in this case, let's use that hue example. So now I've basically generated the hue rendering of this image, and when I'm looking at this, even zooming in, wow, these look really good. There's really no difference in those in this area of the Colosseum. But what does the information look like if I look at the sky? So in this particular case, when I look at the hue area of the sky, it turns out to be black. But you notice that in the image on the right, the one that has hidden information, there is all kinds of distortion that happens because of the information that was changed within the quantized DCT values of the JPEG file. So we can clearly identify that. But what if I want to look at that more directly? Instead of looking at this, again, second order attribute, what if I want to look at the first order attribute, which would be the actual quantized DCT? We can do that by generating a histogram of the quantized DCT values, and we'll make this as big as we can so we can kind of see these. So this creates a waveform that shows, and we can kind of see some differences in the waveform, but they don't seem that dramatic. But I want to focus in on the peak areas of this. So this histogram basically determines what is the DC value in all of the quantized values within the DCT and basically adds them up. So it just tells me how many times that particular value occurred. So in the case of the image on the left, you notice that we have a pretty defined peak. At 169, there were 850, and I can actually show those values. There were 874 occurrences of the value 169 as the DC coefficient for each one of the quantized values. So it's the most significant one that was there. And you notice the two adjacent values are relatively low, 0 in one case and 25 in another. So the occurrence of 168 versus 170 is relatively low. The question is, what happens in the image on the right, the one that we know that contains hidden content? In this particular case, we have a very different structure. We still have that peak at 169, but in this case, there's only 610 occurrences of 169, but you notice that at 168, there's 263, and at 170, there's 10. So those quantized values of the DC coefficient of each of those quantized DCTs changed. This is where the information was added or hidden within this particular image. So the visualization of this allows us to look at the image and render it differently like we did with hue, but also examining the histogram of the quantized DCT coefficients allows us to look at the actual values that were in fact altered within this particular image. Now, we typically use this kind of an application to verify the kinds of things that we're getting from the algorithms because the algorithms do most of the work for us. But this allows us to visualize and look at the resulting data a little bit more closely. So this video provides just a very quick overview of the three basic steps that we take when we're doing analysis of potential steganography use or data hiding use within a system. First, we scan for known steganography programs that may be on that particular system or within a particular directory, as I demonstrated. Once we determine that there is, we would then actually perform a scan and look at all of the possible image, audio, and video files that were on that particular system in order to determine if any of those contain anomalies that would be consistent with anomalies that are caused by data hiding or steganography. And finally, we would actually take any of those hits that we received from the carrier files that were anomalous, and we would actually visualize those and perform some manual analysis of those images or those audio files in order to be able to better look at more specifically the kinds of modifications that were there to again confirm or potentially rule out the potential of hidden data within that content. So hopefully this gives you a little bit of an overview of how the tools work together and the different steps that you would take to conduct a data hiding and steganography investigation. Thank you.